This is our last unit for this year. We're going to start with a very important definition. And this definition describes something that is going to be pretty much the main focus of our last unit, and that is a function. Now, this is a term that you've seen before in Algebra 1 and Algebra 2. So we're going to define it a little more carefully, a little more formally, and then because there is a lot to unpack in this definition, I'll go through this a little more in depth. So a function is a rule, and it's a rule that assigns to each element x of a set A exactly one element of a set B, which we call f of x. Let's look at that a little more closely because some of this might not really be clear. A function f is a rule. Usually by a rule, we mean some sort of formula or equation. And that formula or equation, that rule, is going to take something from one set, we call that x, an element is just a member of a set. So if we have a set of objects, each individual item in that set is called an element. For example, a class of students is a set. Each individual student in that class would be an element. A store, a grocery store, for instance, that is a set of things. Each individual food item or item in that grocery store would be an element. So an element is just an object. So we have some element called x in this set. And we have a rule that is going to take that element and pair it with exactly one element from a different set. And we call that element in the other set f of x. Now, there are two words in this definition that are extremely important. And these two words distinguish a function from things that are not functions. And these are the two words. Every element from A only gets to have one partner from B. The reverse is not necessarily true. Elements from B can be assigned to different elements from A. But elements in A only get to pair with one element from B. And I'll sketch that out in a picture shortly, make that a little more clear. So a function is some sort of rule that takes something from one set and pairs it up, assigns it to something from another set. A couple of other terms that you're probably familiar with. We call the set A the function's domain. And you can probably guess what set B is going to be called. Another term you've probably seen before, the range. This is one semi-formal definition of a function. The more higher level math courses you take, the more formal this definition becomes. This is sort of the fancy version for a high school math course. This would be a bare bones definition for anything above calculus. The functions get more and more well defined as you go up, but on the other hand, the definition also gets more and more abstract and a little more complicated to understand. So consider this definition the top of the line for a high school course. This is This is the most formal definition for that a high schooler will usually encounter. And it's not as abstract as it seems. Everything you did with functions in Algebra 1 and Algebra 2 is in this definition. This definition just puts those concepts into a little more formal vocabulary. So let's take a look at some notation. Here is a function of x. This does not mean f times x. This means function of x. And we don't have to use f every single time. We could use g of x. We could use h of x. We could use any letter we want of x. Or we could even use a different variable. Sometimes you have functions of y. As you increase the number of dimensions you have, say you're talking about a three-dimensional space, you'll have functions of x and y at the same time. Typically, you might see this if you're talking about area. Area is usually capital A of x. Polynomials are sometimes P of x, and so on. F of x, I'll go back to f of x. I'll declare this to be 2x minus 1. And here's how we interpret this. We have a function of x. And here's the rule. Whatever x is, whatever is inside this parenthesis, we plug into this spot. We double it, we subtract 1, and we will get a value. Let's say x is 3, for example. F of 3. 3 is inside the parentheses. I plug 3 into this spot, and I get 5. 2 times 3 minus 1. So I have taken the element 3 from this set, from the set A, and the rule says it's paired with the value 5 from set B. That's using the definition. Here's another function. We'll just call this x squared minus 1. I'll call this, I don't know, 2x cubed plus x minus 3. We could have any kind of function, really. You could have square roots, you could have fractions, you could have all sorts of fun stuff. So let me go back to f of 3 briefly. F of 3. Said that was 5. 3 is in this domain. 3 is in the domain. It's what was inside the parentheses. Think of the parentheses as the domain. Think of this as the range. Another way I can express this, when x equals 3, f of x equals 5. And there's yet another way to represent this, using an ordered pair. When x is 3, y is 5, or f of x is 5. And now I have a way to translate this into a graph. It's a way to visually represent this function. And by the way, this is a function that you will need to know what its graph looks like and what its name is. Same thing with this one. There will be 8 different types of functions you'll need to know by equation and by graph. More on that later. Looking at what we've done over here in purple, we can sort of take this f of x and we can write it in a different form. We can write this as y equals 2x minus 1. A function is often just a fancy way to write y equals. But not everything on a graph is going to be a function. Not everything on a graph is a function. Lots of things are, lots of things aren't. I can take this ordered pair, xy, and I can write it as x f of x. That's really what a y value is. It's a function value. When I plug this into the function, I get the value of f of that function. If any of this is still confusing, make sure you post some questions. Here's another way to look at functions. So here I have a set A. This would be the domain. Here I have a set B, and we already called this the range. Here's sort of what's going on. Let me pick a different one. Here's what's going on with a function. I'm going to take, I don't know, I'll take 5, and I'll pair it with 0. And then I'll take, let's say, -1 is going to pair with -3. And let's say the square root of 2, it's paired with dog. And you can pair anything with anything. Car, I'll pair with truck. So if I'm going to write some ordered pairs here, I could say that I have the ordered pair 5, 0. If x is 5, f of x is 0. If x is the square root of 2, f of x is dog, and so on. And so far I have a function. Every x has exactly one f of x. Every element so far of A gets exactly one element of B. Let's keep going. I will pair 3/4 with 4/7. Every element of A still has one element of B. Blue, I'll also pair with truck. I still have a function. Every element of A still has exactly one element of B. In other words, every element here only has one arrow leaving it. B is allowed to have multiple arrows coming to it. An element of B gets to have more than one arrow. An element of A does not. If I continue my ordered pairs here, we said -1 is -3, 3/4 was 4/7. Blue went with truck, and car also went with truck. If this was not a function, I would have the same x value twice. And if I look at all my x values here, if I look at my domain, I have not used anything twice. It is okay to use y's twice. It is not okay to use x's twice. unless they go to the same exact thing. So in other words, if I take 5 and I draw another arrow to 0, I have not changed anything. Our function, our rule, has to be consistent. In other words, if I put 5 into our rule, it better give me the same value every single time. Think of a calculator that is going to give you multiple answers to the same exact calculation. Let's say you take 200 times 18. You punch that into a calculator, you'll get an answer. And let's say you do it a second time, 200 times 18, and you get the same answer. You do it again and again and again, you get the same answer. That is a function. You are giving it a value, it applies a rule, and you get a result. Now let's say you take a different calculator, you give it 200 times 18, you get an answer. You do the calculation again, only this time you get a different answer. Let's say 200 times 18, you get, 3,600, which is what it's supposed to be. You do it again, 200 times 18, you get 3,600. You do it again, 200 times 18, you get 5. You do it again, 3,600. Again, you get 5. And then you get 5, then you get 5, then you get 3,600. That's not a very reliable calculator because you're going to apply the same rule to the same thing and get different answers. That is not how a function works. A function has to be consistent. So when we have functions, we have not functions. We look for, is there a rule that's consistent? And I look at my sets here, I have a consistent rule. No x will give me two different f of x's. Let me make the rule fail. I'll use red. This will fail. Blue now goes to 0. The rule now fails. This is no longer a function. Because sometimes when I apply the rule, I'll get 0. Sometimes I'll get truck. Sometimes I get truck. Sometimes I get 0. The rule is now inconsistent. This is not a function anymore when that happens. Let's get rid of that because I want this to stay a function. Here's another way to look at that same concept. We call it the vertical line test, something you may be familiar with from Algebra 1. If I take a vertical line, let me get a vertical line here. Here's my vertical line. If I move it across the function, that line should only hit the function or the graph of that function one time. And as I move in here, that happens. This vertical line never crosses the function more than once. So this graph right here is a function. If we had repeated x values, we would have a problem, like we have over on the right here. Here I have a value of x. It's got a value of y. But over here, and I did this before I drew my vertical line, these are all supposed to line up. Let's make that a little better here. Little slate edit. There. Now the rule is broken. Right here we have a problem. Vertical line touches the graph 3 times. So I have the same x value with 3 different y values. That's a problem. In other words, I have a rule that is inconsistent. Sometimes when I give it an x value, I'll get this answer. If I give it the same x value, I might get a different answer. And I might even get a third answer. The same input, I'm doing the same exact thing on the same value, but I'm getting multiple possible answers. That is not a function. If that was a calculator, that would be a disaster. This is not a function. That doesn't mean we can't graph it. That doesn't mean this is an impossible structure. What it means is it's not a function, and we cannot write its equation as a simple y equals bunch of stuff with x and powers of x. It means we potentially will have y's on both sides, and we're unable to simplify that down to a simple y equals. It could also mean some other things. It could mean that this is expressed as a function of x and y, but equal to time. It's got a time parameter. It's the path of some particle over time, and it's expressed as a function of x and y. It is not a function of just x anymore. This is the vertical line test. If a vertical line hits it more than one time, all it's got to do is fail once. Here it failed once. Here it fails here also. It fails here also. If it fails one time, it's not a function. So, put that off to the side. And here's looking at that in terms of sets. I have x1 paired with y1. But now I have x2 paired with 3 different things. And this is what makes it not a function anymore. The term for this is just relation. We have a relation between 2 variables, but it is not a function. Not a function. This x value is only allowed to have one arrow leaving it. Notice that the y's, each y only has a single arrow. And that's okay. Y's are allowed to have single arrows coming to each value, or, as we saw before, a y value can have multiple arrows hitting it. X's, though, are not allowed to have more than one arrow leaving an x value. Okay, now that we have a little sense of functions, here are some that you are going to need to know. You need to know the name of these functions, what their graphs look like, and what their equations look like. And when I say equations, I'm talking the parent function equation. And yes, you should also recognize if things have been shifted or stretched, but you should at least know the parent function from memory. You should know what the graphs look like from memory. So if somebody says to you, rational function, you should have a sense of what that looks like and what the equation looks like. Or if somebody says quadratic, you should be able to recall, here's the general formula for a quadratic, or at least a simple quadratic. Here's what a quadratic graph looks like, and so on and so on. So there are 8 that you need to put into your memory banks. Linear is our first one. We all know what a linear function looks like. Straight line, simple graph. We've all seen this before. It's our old friend y equals mx plus b. There's a linear function. And then the second one you probably learned back in Algebra 1, quadratic. Your favorite quadratic is going to be y equals x squared. And there we have that one. These two should already be in your memory. If not, they need to go there ASAP. Cubic. Probably learned this in Algebra 2. What a cubic function looks like. What its graph looks like. And cubic functions can vary somewhat. The plain vanilla y equals x cubed flattens out here at 0. Some cubics look like this. Some have extremely large humps like that. Those are poorly drawn cubics. There we go. They never really get vertical. So cubics can vary many ways, but the plain vanilla one, a little flat there at 0, and then think of it as a half parabola that goes up and then a half parabola that goes down. Radical. These functions are pretty rad. Plain vanilla is just the square root of x. They start at 0, 0, and they grow slowly like this. Rational. We're going to spend some more time on rationals a little later on in this unit. For now, just focus on the plain vanilla rational, 1 over x. These have lots of different variations. So at least for now, when you're asked to identify or name a rational function, y equals 1 over x will be our go-to. Just a plain vanilla rational function. One half looks like this. One half looks like this. This part here looks like, in fact, a rational function appears to be a hyperbola, where you have curve approaching the y-axis increasing, a curve coming down that's approaching the x-axis, never gets there. The term for this is asymptote. And then we have the reverse, the mirror image over here. As x gets really, really, really negative, it approaches the x-axis again. As x gets really, really, really close to 0 this way, this gets steeper and steeper and steeper. But again, they never get to be vertical. They never actually get there. They approach each axis, but they never cross the axis. Three more. Exponential function. Also notice that instead of writing y equals all the time, I could be writing f of x equals. Since we're graphing, I've gone to the y equals notation, but just understand that instead of y equals, this could also be f of x equals. Those of you taking calculus next year, you are going to see E lots and lots and lots and lots and lots and lots and lots of times. It has lots of applications. It shows up in all kinds of things. You are going to become best friends with E to a power next year. And if you're not taking calculus, don't worry, you will see E in some other math course that you'll need to take for whatever program you're likely going into. Cannot escape it. E to the x. You remember your algebra 2, graph of e to the x kind of looks like this. It approaches the x-axis, never gets there, and then it grows very, very quickly. Actually, that's not a real good. It actually grows pretty fast. We'll get to know e to the x very intimately next year in calculus. Logarithmic. Because we used e for exponential, I'm going to use natural log for the logarithmic because it is the inverse of e to the x. Natural log and e to the x are inverses of each other. And because we're going to see a lot of e to the x in calculus, you will also see a lot of natural log in calculus. Where you see one, you see the other. Can't wait. Notice that because e to the x grows really, really fast, natural log grows really, 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 really slow. Very slow. It's one of the slowest growing functions in existence. In fact, if you go to x equals 1 million, so you have an x value of 1 million, your y value is only 13.8. You have to go 1 million steps to the right in order to go up 13.8. That is not a fast growing function at all. It's an extremely slow growing function. On the other hand, e to the 1 million will overflow your calculator. So let's look at it from this perspective. E to the 13th is a very large number. E to the 14th is also a very large number. E to the 13.8 is just under a million. So on the E graph, if you go 13.8 steps to the right, you've got to go up 1 million. It is the exact opposite of natural log. Natural log takes a million steps to go up 13.8. Exponential takes 13.8 steps to go up a million. One of the reasons they're inverses. Last but not least, the sinusoidal functions. And yes, you will see a lot of these in calculus as well. All in color. And from our work earlier in the year, we know that this is either y equals sine x. We could also say y equals cosine x. Doesn't matter. We know that every sine graph can be written as a cosine graph. Every cosine function can be written as a sine function just by shifting. I'll graph a sine function, but it could also be a cosine function. And there we have it. These are the 8 functions you need to become very familiar with. You need to commit these to memory. Name, equation,